Okay, since we have this event today, let's start. I shortened a little bit of the stuff, and I will glance over several slides, just giving you a reference. So, what is the basic idea of how we propose to analyze DRTs automatically? Is actually presented in this slide. Let us assume that we have two DRTs, and let's focus on here. This is the starting point. We have the blue one, let's call it a reference, and the red one or the pink one, and let's call it the target or the current DRT. Yes, by looking at it, we can immediately see that there is a difference, but the goal is everything, all of this to be done automatically without any human intervention. So the problem is the following. We have to find a matrix P that will say the following. So we have the frequencies of the reference distribution of the reference DRT and frequencies of the target DRT. And this matrix P will tell which the mass that is in this frequency, how it is distributed to all other frequencies. In ideal scenario, when everything can be matched one-to-one, this frequency will be matched to this one to this one, and so on. And this will be like a diagonal matrix, and everything else will be zero. But this is not the case because we have to move stuff around and maybe somewhere destroy a little bit of a DRT or add a little bit of DRT in order to meet the target. So this is the matrix P that we would like to generate. The value C is actually the cost in whatever units we need, saying that the cost is zero if I move frequency X from the source to frequency X of the target. This means that I didn't disperse the frequency to the mass to different frequencies. So I stayed, I made a match frequency to frequency. So this is price zero. If I have to move it around, then I have to pay some price. In the simplest case scenario, the cost is, in our case, the difference between the source frequency and the target frequency. So if I have to move some part of the DRT from 10 Hertz to 15 Hertz, there is a price penalty of 5. Whatever this unit means. But there is another issue that we have here. We know that the DRTs can inflate or deflate. This means that if I take this matrix P that I was drawing here and says I have a distribution mass here like this, and the target was something different, let's say. What I want to do, and this matrix will have some data, how I move here, and so on. This will have some values. If I do the summation in this way, I will get some distribution, which in ideal case scenario, the dotted one should be equal to this one. And if I do a summation of the matrix in this direction, here I will get a dotted red one. In an ideal scenario, the dotted DRT should be equal to the starting point. And by these measures, we are calculating how much the difference occurred. What do these two parts of the equation tell us? They tell us how much of the DRT we had to destroy, we don't have a place where to put it, or how much we have to create a new one. So this is the mathematics behind It might be it might be for you that I'm pushing it rather abstract, but now I'm going to go on actual examples. You don't have to worry about how this works. Everything is implemented by a library that is called unbalanced optimal transport. I will show it to you. So finding a minimal solution of this problem here is rather complicated. And the algorithm for optimization is called Sinkhorn algorithm. This is the PDF that shows a really, really nice and gentle introduction how this algorithm works. For the sake of time, I'm not going to discuss it now. There are 2 slides that describe them. I strongly suggest interested readers to visit this PDF. Everything is there. At this moment, all you can do is just trust me when I tell you that this algorithm finds the optimal value of this matrix P. That is the only thing what we have to take into consideration. So, what do we have? Where can we apply it? So this is a result of solid oxide electrolyzer, I think, or it's a solid oxide fuel cell that was tested in Grenoble in France in Centre Énergie Atomique Institute. This is something that we have published. Here you have our paper that doesn't cover the problems of unbalanced optimal transport, but has a nice description of the experiment. So what happened was, the goal was to run this 6-cell stack for more than 3,000 hours and check its degradation over time. This is, on the left-hand side, is how we performed the experiment, so how we did the measurements. So we had an electronic load that was actually used for performing excitation and keeping the steady state operating conditions. We measured current with the current probe and measured here every cell voltage separate. So these are the cell voltages over time, over 3,600 hours. What is listed here are 8 events that happened during the experiment. The first one here is a running period. So as you can see, the voltage of a stack dropped from something about 0.9 volt voltage of each cell, dropped from 0.95 to 0.8 during the running in phase. Then we entered a nominal phase of operation here. And then we come to event number 2. This was done by us on purpose. The goal was to check how the stack performs under different fuel utilization rates. So I can't remember from the top of my head, but I think that we started somewhere from 77 and we went all the way up to 95 or 92. Please don't take the numbers that I'm saying now at the face value. I can double check, but there were 4 steps of increased fuel utilization, and then the cell was returned to a normal operation, the identical as here. It was operated for another time, and then we come up to event number 3. We repeated the same steps of using different fuel utilizations, and the team at Grenoble didn't realize that the hydrogen fuel tanks are running empty. And when we were on the highest fuel utilization step, we suddenly starved the stack of hydrogen. it went into emergency shutdown. This is the first X. And when we restarted it, we realized that cell number 3 is not behaving as it should. So it recovered a little, but never fully. And then matters turned worse. So event number 5, it was, so all the events forward, I'm going to explain each and every one of them, were not our fault. So event number 5, there was a severe thunderstorm in Grenoble, and everything went into emergency shutdown. Then event number 6, again, we missed the alarm that the fuel was low. So again, it went into a fuel shortage. Event number 7, it was planned. As you can see, it was gradual shutdown. We had to move the experiment to a new building. And event number 8, again, fuel shortage. And someone might ask, okay, after the first one is your fault, the second one so-so, but come on, 3 times? Don't you know how much hydrogen you have? Well, anyway, that is the experiment. So the basic thing, what we actually, although one might say that the experiment was a failure, actually it wasn't from my point perspective, because we had a cell that failed, never recovered, and gradually degraded over time. And after the last shutdown of hydrogen, even some different cells here start to degrade a little bit. So for each, so we were doing ice curves, I think, every 12 hours. So there are more than 300 ice curves of this experiment. Everything is loaded, or no, even more. There are 600 ice curves of this experiment. Everything is loaded in the on the repo. You can download it. Those are the same 600 ice curves that I was showing you yesterday or the first day for the DRT calculation. Now we're going to do a proper analysis of those. So, okay, here are the fuel utilization numbers. So from 77 to 92%. And for every ice curve that we have, we first did Kramer-Kronig test. And this is where we realized that we have a problem with the data acquisition, and everything above 1 kilohertz was problematic because of the data acquisition. So we removed this part due to faulty measurements. And in higher fuel utilization, we had to remove some parts in the load frequencies. So what I wanted to say now is that everything that is done from this point onwards uses only the data that has valid ice frequencies. So what we did was, after everything was shut down at the end, after 3,600 hours, the manufacturer, we cannot disclose which one was it. It's a European one. They took the stack and did a post-mortem analysis. So this is the problematic cell. They marked it as number 4 because we were counting cells from different sides. This is the cell that was problematic, but they were counting from here. So 1, 2, 3, 4. And we were counting from this side 1, 2, 3. So on this experiment, even the counting to 6 was problematic, as you can see. But anyway, what you can see on the photo is that the black-gray nickel layer actually became green nickel oxide. It was on the exhaust side of the cell, and this was due to the emergency shutdown. I guess some sealant broke, but we anyway continued with operation. So these are the data of the equivalent circuit models. We feed it a model with 3 RQ elements because in the DRT we found that there are mainly dominant 3 peaks. yes, maybe it could have been done differently, but this is not the focus here. What I wanted to say is that we can see these are the parameters of the this is the second column for the second second time constant was mostly affected, and this is the serial resistance of this cell of the fourth one, the second pole, and so on. And we can see that it was affected all over the place. So what we did here is we calculated the DRT acquired ice curves. There are 600 of those DRTs, and as you can see, we are going only to 100 hertz. That is because we have to cut this part as not valid. And due to limited data acquisition at the time when we were doing, one might say that the frequency band is not wide enough. I agree, but this doesn't affect what I would like to show you now. So on the left-hand plot, you see a DRT results as one would like to see. These parts here, the huge jumps I will show later, are in the corresponds to the regions where high fuel utilization was done. And you can say, yes, it's clearly visible. You don't need any rocket science analysis to see that this is different. Yes, of course. On the right-hand side, we see the same DRTs, but without the regularization. We can see that the right-hand DRTs are really fuzzy, spiky, and if I showed you only this part of the picture, you will not, none of you will say that this is a DRT plot. Or if it says, then it is a very, very bad. My message that I would like to convey to you today is that you do not need to care about regularization if you analyze multiple ice curves, because it doesn't affect this algorithm at all. So let's see the results. What we did now is, because at the beginning, as I said, there was some running period. This peaks here. So what we said is, okay, let's say that the 10th ice curve, which means that after maybe 48 or 96 hours of operation, somewhere here, that is a fault-free nominal position. Now the system is properly heated up, all the voltages are stabilized, and we can say that this is the way how we want. This is actually a healthy system. That is the thing that we would like to see. That is the nominal state. And then we said, okay, this DRT at this point will be our reference DRT. And we are going to take every other measurement and compare it to this one and calculate how, and actually using this optimal transport, we are going to calculate the price, the cost. How much does it cost to change the DRT from here to become a healthy one? What should I do? Should I expand it, press it, whatever, in order to make it look like the healthy one? And each of these operations have some cost. And this cost is plotted here. So the plot it was done using the smooth DRTs and the fuzzy ones. And the results are visible here. So the blue lines are the smooth curves, and the orange line are the fuzzy curves. And as you can see, they're practically identical. Yes, there is some fuzziness here. I'm going to explain where it comes from. But most importantly, what we can see is we can see that we have identified the first event of fuel utilization here. We even identify the place where the running phase was done. The second fuel utilization, the places where the curve was degrading, and take into consideration that the DRT analysis doesn't take into effect serial resistance. We only see the changes in the time constant. We can see this part. We can see the second shutdown, the next shutdown, the last emergency, and we go on. So even without regularization, so we were analyzing this mess of data, we are getting exactly the same results. That is why I said on Monday that if you are doing a characterization of your material in a laboratory and you would like to know what type of characteristics has this sample, you have to do it with regularization, with everything. But if you do online comparison of results, you don't have to care about it. Just leave it as it is. It will make all these spurious spikes, integrate it, put it through this optimal analysis curve, and you will get this. But we can go even one step further, because telling you that there is a significant change from the nominal position, one can do simply by looking at the voltages. We don't need anything. We measure the voltages and we can clearly say that this part here is different. We don't need any analysis. We don't even need ice curves. That is correct. So what I did actually, I recreated this image through a huge processing machine. But having DRTs means that I have access to the frequencies. And I can check which frequency ranges were mostly affected. See this. I can take, so these are these cumulative DRTs, the smooth ones and the fuzzy ones. The shading from light gray to dark gray represents time. So these one here are the earliest, and the dark are the last one where everything degraded. And I can use this Wasserstein distance that is actually built into this result to see in which frequency bands the changes in the DRT occurred the most. And these are the results. So this is time, and these are frequencies. And the 10th DRT is a reference one, and we take each and every one and compare it to the reference one. And this blue plot shows the results. So we see that in this area, there are no changes in the DRT and consequently in the ice curves because it's the same. Then we have the first fuel utilization, and we can see that these frequencies around 10 Hertz were mostly affected. Then we went into a nominal stage, and more or less everything returned to normal. Then it happened the second fuel utilization. We can see this change in the same frequency band. And then we had the emergency shutdown. And from this point onwards, the third cell never recovered. And we can see that in this frequency band is where the change was mostly affected. After the second emergency shutdown, this frequency band expanded a little. So if we draw a DRT, it is in these frequency bands that this time constant expanded the most. And we can do this online. So every time a new measurement occurs, we will draw a new line here. And slowly this image will grow towards the right-hand side. And we don't even have to look at the DRTs, don't have to do it. Everything is done automatically. There is no training because we are comparing the current value with one that we as experts decided to be a reference. So let's do it. Let's go one step further. Let's see the details. So I'm not showing smooth DRTs anymore. So these are the fuzzy ones without any change. And my question is now, looking at this figure, which frequency bands were mostly affected? And the optimal transport algorithm gives me this matrix. This is the matrix P that I was talking about. And in ideal scenario, this would mean that everything from 10 Hertz went into 10 Hertz. And this should be a straight line, which in high frequency part more or less is. And then we come to some parts around, in this case, from 0.1 to 1 Hertz, where something strange was happening. This is where these two DRTs are mostly different, because this part here was distributed predominantly here. And this is the case. So we have mostly, I will do it like this, mostly white, mostly blue here, had to be distributed somehow to a missing part here. And although this is everything fuzzy, a human person, for a human person, this is really difficult to see. Using this approach, just provide us with this spike here and tell us where the change is the mostly expressed. And actually, when we do DRT analysis, we would like to find which frequency band is mostly affected. And this is what we are getting. So here are the same results, now a little bit more clear. I did it on purpose. So this up here is without regularization. This is the matrix. And this one here is with regularization. So if I showed you this photo, you would this figure, you would immediately say, look, it's clear that in this part, the blue one and the orange are the most different. And I can see that this time constant was mostly affected. This was somewhat affected. But if I showed you this figure, you wouldn't be able to say anything. The optimal transport matrices are more or less identical. But in this case scenario, it was on your own to decide what kind of lambda regularization you will have to use, which frequency bands, and everything that you have to decide when you do a DRT. Here, you don't have to do anything. Just leave it. Whatever comes out, whatever garbage comes out, it will sort itself. That's the idea I would like to tell. So what can we do even furthermore with this DRT? So we would like to see whether in which frequencies the biggest changes occurred. And we can, as I showed you previously, this matrix P, I can sum it in this way and see the changes of the target. And I can sum it this way and of the reference. And I can sum it this way, I can see the changes in the target. And these are the results. So saying I would like to go from orange to a blue one, and the changes is I used up all the mass in the blue one because the orange was expanded, and I have to expand the orange in these frequency bands. This is the non-regularized, and this is the regularized version. But I don't need to see these smooth curves, because even this is going to tell me that these frequency bands are mostly affected. And this is all the information that I want. In which frequency bands is my ice curve mostly different? And I'm getting it with both approaches in exactly the same way. This one is far easier to be performed. We can go even further. I'm not going into more details because I would like to show you the example. Everything is built on a toolbox called Optimal Transport. It has everything implemented inside. You don't have to do anything. All the mathematics is there, all properly numerically implemented. Everything is spot on. What I'm going to show you now is how we can analyze these 600 DRTs and regenerate all the figures. So let's do it, and we'll be spot on with time. So day number 3, this one. We start the kernel. You have here in the notebook, you have extra information. If someone wants to know more about unbalanced optimal transport, these are not my papers. You should check this. This is the paper that describes the experiment. Is the same 600 DRT curves that we were using on day 1. So it's nothing new. It's the same data set over and over again. And you can check it. So let's try this. So I'm loading the experiment data. Here are the DRTs that were calculated. So I will calculate the cumulative DRT, which is solving this integral. It's nothing, it's just cumulative sum. And here is the figure that you already saw with the problematic part. And now the unbalanced optimal transport. So, right? It should be done fast. Right? Solving chunks. So, because it is, I have rather peculiar hardware here. If you have a GPU, this will be really, really fast. I have some strange form of GPU. That's why I have to check whether I'm on Mac OS or not. So let's try it. So now I'm analyzing all these mathematics that I've told you of 600 ice curves with regularization. This is how much it takes. So 600 of them. They are divided by chunks of 40. So for the analysis of 600, it was 35 seconds. Without regularization, it will take more or less the same time. Doesn't affect. I just want to show you that you can regenerate everything what I've shown here from the data that is in the repo. Another 35 seconds, I guess it will be, more or less. Yes, and now I will plot all the results that we had. Now this is zoomed, so it is this figure. It is this figure just zoomed in the first 600 or 800 cases, and then we can just see each DRT particularly, calculate its distance. There it is, and get all the matrices. And so everything that you need to do this analysis on your own DRT curves is contained within this notebook here. And I'm not going to analyze the figures one more time. It is exactly the same thing that I was talking over on the slide.